The next kind of continuous system that we'll analyze is a beam or a column in longitudinal vibration. In this type of system, if our beam or our column is oriented with its longitude along the x-axis, let's say, we are analyzing the motion that is along that x-axis, is not experiencing any sort of deflection about the z-axis. That would be a beam in transverse vibration, which we'll do in following section. For this analysis, we'll start with the most general case of what the beam could look like, what its area could be, what its properties could be. But then, like we saw with strings, we're going to add some limitations and constraints so that we can get a PDE that we will be able to solve. So if this is the general shape of our column, what we're going to look at here is just an infinitesimal slice of the column that we can then analyze further to get our partial differential equation. So I'm going to take this differential slice that has a width of dx, and that is what I'm going to put over here and blow up to be larger. And I will define some of our degrees of freedom here. We are looking at this column having only an internal normal force P, like we saw with the string. In this case, because it is only experiencing this internal normal force, we are not going to have an internal shear force. We are not going to have an internal bending moment. And we're going to define the left degree of freedom here as having some motion u, or some deflection u. We'll define positive to the right, and u will be defined as its deflection from its equilibrium position. So a positive u is the left side traveling to the right of its equilibrium position, and a negative u traveling to the left. And we're going through this very small slice dx, so we are going to presume that the right side is going to undergo a very similar, a very close amount of deflection, u, plus a little small difference as we go left to right of du. And that du can be positive or negative like we saw with the string. And the same thing with the internal normal force. We're going to presume the left side has an internal normal force P. As we go slightly to the right, that internal normal force will only change by a tiny amount, dp. So we'll get to looking at the sum of forces acting on this system, but we're already going to impose some limitations on the types of longitudinal vibration that we'll be looking at here. So first, we are only going to look at systems that are undergoing linear elastic deformation. So we're sticking in that linear elastic region. We are below the yield strength of our material, and when we're in tension or in compression, and furthermore, when we're in compression, we are making sure that we are not buckling our column. Drawing back from strength and materials, we know that when this is the case in the linear elastic region, we can relate that internal normal force P to the stress in our material. That it's typically P over A equals our sigma, our internal normal stress. But here I've expanded out and said that P is sigma times A. And we know materials property-wise that there's a relationship between the normal stress in the material and the normal strain in the material, epsilon. In the linear elastic region, they're related by the Young's modulus, E. And we know that if we multiply the Young's modulus times the normal strain, epsilon, we are going to, in this region, get to our internal normal stress. So P is also then equal to Young's modulus times epsilon times A. And finally, based on our coordinate system here, I'm defining u as this motion from equilibrium left and right. So really the net deformation of this infinitesimally thin piece, if the left side is moving u, the right side is moving in amount u plus du, then the difference in how much the right side moves to the left side moves is du. So that is the change in length of the element, and we know that normal strain can be defined as the change in length over the original length. So if the original length of our section was dx and it deformed an amount du, then du divided by dx is going to be that normal strain. And we are going to refer to that as del u del x because that u is going to change not only with time, but with space. So it's going to be partial u partial x is going to be the definition of axial or normal strain. We are going to be able to differentiate u with respect to time as well, because u, the deformation, is going to be a function of space and time. So with that limitation giving us this relationship between the internal normal force and the axial strain, we now can look at this free body diagram of our infinitesimal slice. And what I want to do is I can sum forces along the x direction for this element. In this picture, we're going to see we have the internal normal force on the left-hand side and on the right-hand side. And not pictured here, but I will include it in the equation, is I can have some external axial force acting on the section as well. So if I sum forces on the left-hand side, to the left, I will have P, so a negative P from the left-hand side of my cut surface. I have a P plus dP on the right-hand side, and again, not pictured here, I have some distributed axial load F times the length dx. Again, in a similar way we had it for the string, although this way F is pointing left or right, since I am only having axial forces acting on this object. So I can do some simplifications here. What I can look at is on the left-hand side, I have a negative P and a positive P, and those are going to cancel each other out, leaving me with this dP plus F dx on the left-hand side. And like I saw before with the string, this dP term, I am going to be able to rewrite, and I can rewrite that as del P del x times dx. And those are going to be equivalent to each other. And plus the F dx, and then the right-hand side. Now the right-hand side is going to just be m times a, because I have sum of forces equals mass times acceleration. So looking at this differential piece, how do I calculate the mass of it? Well, so this differential piece is going to have some cross-sectional area A, and potentially, like we see on the left-hand side, we could have a situation where the cross-sectional area changes as we go left to right. So A could be a function of x, our position along the horizontal. And possibly it could also change in time. Again, if we had maybe like a thermal element to this that changed in time, we could see the area shrinking and growing with time. And if we say that our material has some density rho, and in this case, that rho is a volumetric density. So it's going to be in like kilograms per cubic meter when we are dealing with these longitudinal vibrations. So it is different than what we saw with strings. We used there a linear density. Here it's a volumetric density. And our differential piece here has a length of dx. So now note, because it's volumetric density rho times area, which is going to be a squared length, times dx, which is a length, we have a mass per cubic length times cubic length gives us rho a dx is the mass of a differential element in our system. Then we're going to multiply that by the acceleration. Well, the acceleration is going to be our position or our deflection u. The second time derivative of it, the second time derivative of position, gives us acceleration. So again, u is a function of both space x and time t. So here I'm taking its second derivative with respect to time. And if we look at the equation now, after we cancel out those p's, after we've defined our right-hand side, I have a dx on each of the two terms on the left and the term on the right. So I can simplify that down, I can cancel out the dx's, and I will be left with this expression. So from summing forces and taking that Newton's second law, I have sum of forces equals mass times acceleration, and as I did at the beginning, limiting this to the linear elastic region for deformation, I have a relationship between the internal normal force P and the axial strain. So what I can do is I can take these two properties, these two equations, and put them together. For P in my equilibrium equation, my F equals ma equation, I can substitute in that constitutive equation for P. So if I do that substitution, I am going to be left with, now I have my del x of P replaced with Ea del u del x, plus my F of xt equals rho a del squared u del t squared. So I wrote it here in kind of the most general way, where potentially my material properties could change along the length of the column because maybe it is a non-homogeneous material. and possibly they could change in time. The density of the Young's modulus could change in time if there was a temperature change happening or a magnetic field or something like that. So potentially they could be functions of space and time. The area could also be changing along the length. If it's a non-constant cross-section, the area could change in time, again, maybe due to a temperature change that would expand it or contract it. And that distributed axial loading could change along the length, and it could be dynamic. It could change in time. But so that we can analyze this, so that we can get a closed form solution, we are going to limit a lot of these changes that we would be seeing. So we are only going to look at systems here that have a constant density, a constant material, and constant cross-sectional area. And this is going to be constant across space and across time. So what's this going to change in the system? Again, we're going to say that Young's modulus, which is a material property, does not change in space or in time. So I'll just get rid of the function part of it. The area is going to be constant in space and time, and our density, and again our area over here. So it's just going to be rho and A and E and A. On the left-hand side, if E and A are constant in, well, here space is all that's going to really matter, I can pull them outside of the differentiation. So I can have EA on the outside, so all that's left on the inside is that del U del X. And if I do that, then I can just take the partial differential with respect to x of del U del X, and the left-hand side, I'm left with then the second derivative of U with respect to x. And on the right-hand side, the rho and the A are now constants, so I can just rewrite them as rho and A. Okay, so starting now with this relationship, we want to simplify it further. We're seeing that we have the makings of a partial differential equation here. We have a U term on the left with respect differentiated with respect to x, and on the right-hand side we have that U but being differentiated with respect to time. For the closed form solutions we're going to be seeking, we're only going to consider free vibrations in this course, which makes F equal to 0. Which then further simplifies this, that now the left-hand side has the del U, del X terms, and the right-hand side has only del U, del T squared terms. So I can simplify this because once F is 0, that also means that I can cross out the A's on the left-hand and the right-hand side, and I can divide both sides by rho. And I can then write this partial differential equation as this C squared del squared U del X squared equals del squared U del T squared, where C is going to be defined here as the square root of E over rho. And if we see the highlighted portion, it looks nearly identical to what we saw for the string problem. The only difference is going to be that we're using U, which is that horizontal deflection, rather than W, like we used for the string, which was denoting the vertical deflection. However, the form of it otherwise is exactly the same. It's a second order differential on the left with respect to space and a second order on the right with respect to time. This C constant is going to be the Young's modulus over the volumetric density. So again, rho here is volumetric density, and in the string it was linear density. And because the PDE is in this same form, we're actually going to be able to solve it exactly the same way we did for the string problem. One thing we will have to think about a little bit differently, again, is this degree of freedom we're tracking U across the entire length of this column is the horizontal displacement, not the vertical. So when we're thinking about the boundary conditions, it's going to be on the horizontal displacement, where do we know it, or the axial strain, the U prime, where do we know the strain's value. And we're going to be limiting our analysis, just like for the strings, we're going to be limiting it to boundary conditions that are homogeneous. So specifically in this course, where do we know the displacement is set to 0? Where do we know the strain, the axial strain, is set to 0? So we've actually already gone through the steps of solving this partial differential equation. So just as a summary, when we have a column type of problem or a beam in longitudinal vibration, First, we need to identify that system as being a column or something in longitudinal vibration. So is it deflecting along its longitude only? And do we meet the criteria to have that partial differential equation from the previous slide? Are we operating only in the linear elastic region? Are we not buckling our column? Do we have free vibration? Is the cross-section constant? Are the material properties constant along the length and also in terms of time? And if all of that is true, then we can start with that PDE as our governing equation. If any of those limitations are not true, then we are going to have to use a different solution process to find our U of xt solution. And we might have to use a finite element analysis in order to do that if we can't get easily a closed form solution. So let's say we do meet all of those criteria, we then can find an analytic solution to this problem. And then the steps look basically the same as what we saw for the string problem. We're going to start by finding that U of x, and we're going to need to identify our two boundary conditions. Where do we know that the axial deformation is 0, and or where do we know that the axial strain is 0? We're sticking with, again, homogeneous boundary conditions for our analytic analysis in this course. So we can use one of those boundary conditions to find that A constant or B constant is going to be equal to 0. And that's going to happen when we have these homogeneous boundary conditions. The other boundary condition is then going to allow us to find our natural frequencies, the same way we did for strings. We're going to find that omega n. We've already found that A or B is going to be 0, so we can put that together to find our eigenfunction U of x, or really U sub n of x, because we have an infinite number of eigenfunctions associated with each of our infinite natural frequencies. Then we can start to put together our total solution, because it's the eigenfunction times the t of t, and t of t, if we remember, is going to have this coefficient c sub n and d sub n. So we want to find those using our initial conditions. So what at all points in the beam are going to be the initial conditions? What's the initial position of every point in the beam when time is 0? And what is the initial velocity, horizontal velocity, in the beam or the column when time is 0? So we need to apply those initial conditions, and then we can find the coefficients that go along with our time solution. So finally, once we have all of our eigenfunctions, once we have all of our natural frequencies, and we have found those coefficients c and d, we can put them all together and we can write the infinite sum that is the solution to U of xt. That is the U of xt that solves the partial differential equation that we were able to define for our longitudinal vibrations. Now, in these problems with these boundary conditions, there's really only a couple of boundary conditions we can even have, because it's only going to be where do we know that the deformation or the deflection is 0, where do we know the axial strain is 0. So these are really the only ways that we could have our longitudinal vibration happening, or the boundary conditions for them happening. We could have a fixed free beam, and we'll go through the derivation, but this is what we're going to be getting in the end. So these would be the boundary conditions. Here they're using theta to be what we use as U, the horizontal displacement, and this is from the book, from the textbook. So at the fixed end, we know that the deformation or the deflection has to be 0. There cannot be any deflection where it's fixed to the wall. And that's true for all points in time. And we also know that at the free end, at L, we can have no axial strain. It's a free end. It cannot be in strain. So those would be those two boundary conditions. And as we apply them in solving for that U of x, we're going to be able to find our natural frequencies and the mode shape, which would also be our eigenfunctions. And we see that the natural frequencies are going to change based on the boundary conditions. If we have a free beam, which would be capable of translating, we typically don't have a free beam. More likely the other way that our beam could be have our boundary conditions as being fixed. So notice the boundary conditions are different. On the left side, still the deformation is 0, but now on the right-hand side, the deformation is 0 rather than the strain being 0. And we're going to see as we go through the steps of finding our natural frequencies and our mode shapes, the natural frequencies are different when we have a fixed end. Even if it's otherwise the exact same beam, changing the boundary conditions changes our natural frequencies. And in turn, it's going to change the eigenfunctions. So the behavior of the beam changes when it's a fixed free versus a fixed versus also a free. And those are really the only ways that we can have boundary conditions, homogeneous boundary conditions, in our beams when they're in longitudinal vibration. We're going to see when we look at transverse beams that we can have a lot more types of boundary conditions, so we can have a lot more types of natural frequencies and eigenfunctions in those types of systems. But it's a good habit to still go through and derive your natural frequencies based on the boundary conditions that you have in your system, and then use those natural frequencies to define your eigenfunctions or mode shapes.